Hey everybody, welcome to another mini lecture in complex analysis. In this one we are going to talk about antideratives of holomorphic functions. So let's look at it. We have a simply connected domain, so simply connected is important. I will tell you in a moment why this is important. So we have a simply connected domain which I have called D, and on this D we have a holomorphic function f, right? So f is defined on D. Is holomorphic, and we want to define an antiderivative. So this is a function which we'll call big F, and this big F is supposed to have the property that the derivative of big F is small f, right? Just as you are used to. And to do this, we make the following definition. We define f of z as an integral, which is not so surprising after all, f w dw, and we are integrating along a way gamma z. And what is this contour we are integrating? Well, this is the following. Inside our simply connected domain D, we pick an arbitrary point, which I have called z0. So we pick this point, and now to evaluate this integral here, f of z, we simply integrate an arbitrary way going from z0 to z. So let me hint a way here, just in dots. Because it doesn't matter which way we choose. We pick any way from z0 to z and integrate along this, and we call the result f of z. And now you may ask, why are we allowed to do this? Because as you know, in the complex plane, there's more than one way in general in going from to go from one point to another. So we might go this way from z0 to z, or we might go this way. And the good news is, because we have picked our domain to be simply connected, it doesn't matter. Everything is well defined. We just pick an arbitrary contour, and the integral is well defined. This is because the integral along every way from z0 to z is the same as the integral along every other way. And this is a direct consequence of Cauchy's theorem, which says that if you're talking about a simply connected domain, and this is why we have chosen one, if you're talking about a simply connected domain and you're integrating along a closed contour, then the integral is zero. So in other words, when you start at z0 and go from z0 to z one way, and you pick another way to go back from z to z0, then this is a closed contour, and the integral along this closed contour is zero. And this means that the integral along one way is minus the integral going back the other way, or still in other words, both ways have the same integral along the way. So this definition of f of z is indeed independent of the way we choose to go from z0 to z. So we are allowed to make this definition. And now things become easy, because now we want to look at the derivative of f in an arbitrary point a in D, and we want to see that the derivative of big F is indeed small f. So first note that because D is open, right? D is a domain. Every domain is in particular open because domain means open and connected. So D is open. This means that around this chosen point A, there is at least a small ball of radius epsilon, such that this epsilon ball is still in D. And this means that we can look at the derivative of our function big F. So let's now focus on A and some point Z, which is in this epsilon ball. And let's first look at the quotient f of z minus f of a divided by z minus a, and subtract the value of f at a from this. And let's take the absolute value of this whole expression. And now we can say this is the same as the integral along this line from a to z, because f of z is by definition the integral from z0 to z, and as I've told you a minute ago, it doesn't matter which way you choose. So in particular, you can choose the following way, which I have drawn here. You can choose this way, going from z0 to a, and then to z. And of course, going from z0 to a is what we call big f of a. So the difference between these two, between f of z and f of a, is just the integral along this line segment here, so which I have called line segment from a to z. So this is this integral here, fw dw, and everything else stays the same. We still divide by the absolute value of z minus a, and we still subtract the value of f at the point a. And now we can use the ML inequality to say that, so let me just remind you of the ML inequality. Well, in case you never heard of it, please look it up, or have a look at a video I have previously uploaded here on this channel. This says that this integral, well, it must be smaller than the supremum of the values taken on the interval you're looking at, you're integrating over, times the length of the interval, right? So this is a very intuitive result, and this is called the ML inequality. So we can use this inequality to say that this integral, well, it must be smaller or equal than or smaller than 1 over z minus a times the supremum of fw minus a, where we are taking the supremum over all values for all w in this line segment from a to z. And of course 1 over z minus a and z minus a, so this is the length of this interval, right? This has length z minus a. So this is this comes from the ML inequality, and this cancelled with this. And now if you if you consider z going closer and closer to a, then this becomes a derivative, and we see that this expression here in this absolute value tends to 0, and what this means is that this derivative, or that the difference between this derivative and the value of f at a is 0, and in other words, the derivative of f at the point a is just small f, and this means we're done. We've found an antiderivative. So that's all for this mini lecture. Thank you for watching. Don't forget to like and subscribe, and see you next time.